All right, in homework 3.7, we're doing optimization. I'll do a few of these problems with you. The first one, an open rectangular box. I'm going to start by drawing a picture of what that looks like. There's some kind of a box. I don't know. This is my attempt at drawing a box. And there is no top. The top is open, so it's blank. Cool. An open rectangular box with a square base, so all of these sides are the same, is to be made from 48 feet squared of material. So the surface area is 48. This is the surface area. That's how much material we're using. What dimensions will result in a box with the largest possible volume? So the first thing we're going to do is we're going to write an equation for the volume of the box. The volume of the box is going to be, I'm going to call this x, and since the sides are the same, this is also x. And then this will be y, because it doesn't say that the height needs to be the same as the length of the base. It just says that the base is a square. So the volume is length times width times height, which is x squared y in my picture. And also, we know that since the surface area is 48, we need to get down to one variable before we take the derivative. So to get down to one variable, we need to write an equation for the surface area. The surface area is going to be the base is x squared plus each of these sides is going to be x times y, x times y, x times y, x times y. So it's going to be 4xy. So that's the base and then the four sides. And that needs to equal 48. I need to find a variable I can solve for, and since there's two x's, I'm not going to solve for x, I'm going to solve for y. I'm going to get y by itself. So 48 minus x squared, and we're going to divide by 4x. And that's going to be substituted into here. So the volume is x squared times 48 minus x squared over 4x. When I multiply, one of the x's I am multiplying by will cancel out with one of the x's I'm dividing. So this simplifies to x times 48 minus x squared over 4. And the x will multiply times the numerator, giving me 48 minus x cubed over, 48x minus x cubed over 4. That's the volume, and that's what I'm trying to maximize. Now, when I take the derivative of this, notice that the 4 is just the same as multiplying by 1/4. It's a constant. 1/4 times 48x minus x cubed. I'm just going to leave it like that. So, to maximize it, we find the derivative and find the critical values. So, the derivative is, leave the constant alone. And the constant multiple rule says we just leave the constant and multiply by the derivative of this. So 48 minus 3x squared. We want this to equal 0, so I'm going to go ahead and factor this. I can factor out a 3. So I get 3/4 times 16 minus x squared equals 0. 3/4 times 4 minus x times 4 plus x equals 0. So x equals 4 is the only critical value. I have two options. I could either try to find the endpoints and do the candidates test, because we are looking for the absolute maximum, or I can show that since this is the only, -4 is also a critical value, but it's not possible for the length of a box to be -4. The minimum value of a box length is 0, so that's not a possible thing. This is the only critical value. And so I can also use the first derivative test when there's only one critical value and show that it's a maximum, and I'm going to do that instead. So when x is 4, the derivative is 0. When x is a little smaller than 4, like 3, we get a positive times a positive, which is a positive. When x is a little bit bigger than 4, we get a negative times a positive, which is a negative, so this is a max. And so the length of the base equals 4. That's what x was. That is one of the dimensions. And we need to make sure we're actually answering the question here. It says, what dimensions will result in a box with the largest possible volume? So that's only the length. We also need to find the height of the box. And so I'm going to plug into this surface area condition because I know this is a relationship between x and y, and if I know what x is, I can find what y is. So I'm going to plug this in and say, oh, I'll just use this. Y equals 48 minus 4 squared divided by 4 times 4. So this is 32 over 16. Y equals height, and that comes out to be 2. So these are the dimensions of the box that maximize the box's height. All right, do one more, I guess. Let's see, a sheet of cardboard 3 feet by 4 feet. So there's a sheet of cardboard 3 feet by 4 feet. Will be made into a box by cutting equal size squares from each corner and folding up the 4 edges. So they're going to cut out squares from the corners and then fold up the edges to make a rectangular box. Okay, and we're trying to maximize that box. So again, this is actually going to be very similar to number 1 in that the shape it ends up making when you do that is going to be a box with an open top. Here's the top. And we need to figure out what's going on here. So it says that you're cutting out equal size squares. So I'm going to call this x. This length right here is x, and that's the same in all of these places. These are all x. Okay? And so when I eventually fold up the box, here's the base of my rectangle. That's the base of my rectangle after I cut out x. And so I need the length. What is the length of this base? Well, this length was 4 feet, but we cut out 2 of these corners, so this is now going to be 4 minus 2x. This length was 3 feet, but we cut out 2 of these corners, and so this length right here, which is this, is going to be 3 minus 2x. So those are those. And the height of the box, when we fold it up, well, that's whatever length this is. Like we can see that this length right here is x, and that's the height. And so that's what we want to maximize. We want to maximize the volume. This only has one variable, which is really nice. So the volume is length times width times height, 4 minus 2x times 3 minus 2x times x. Instead of doing a triple, I could do a triple product rule when I do the derivative. I actually don't like it. I'm going to instead just multiply this out before doing the derivative. So we get 12 minus 14x. I sure hope we get minus 14x plus 4x squared times x. V equals, I'm going to multiply the x out and rearrange. 4x cubed minus 14x squared plus 12x. I put the 12 in the back and the 4x cubed there. So the derivative is 8x squared minus 28x plus 12. And we want to find the critical values here. There's a 4 in all of these, so I'm going to divide by 4. 2x squared minus 7x plus 3 equals 0. And so this factors into 2x times x minus 3 minus 1. So x equals 1/2, x equals 3. Notice that if x is 3, that's not possible. X is 3 isn't possible because this side was 3 feet, and we would have to take out 3 twice. Well, that's not there. This side was 4 feet, and we would have to cut out 3 twice. That would get you down to a side length of -2, and that's not possible. So x equals 1/2 is the only critical value that makes sense. So again, we're going to make a quick sign chart and say when x is 1/2, obviously this derivative is 0. When x is a little bit smaller than 1/2, when x is 0, this is positive. When x is bigger than 1/2, like 1, this is negative. And so this is a local maximum. And so the dimensions are going to be x is 1/2. It asks for the dimensions of the box. The dimensions are, since x is 1/2, the length is going to be 4 minus 2 times 1/2, which is 3. The width is 3 minus 2 times 1/2, which is 2. And the height is 1/2. Those are the dimensions of the box that have the greatest area. Sorry, you guys couldn't see that. I apologize. So again, when x is 1/2, 4 minus 2 times 1/2 is 3. 3 minus 2 times 1/2 is 2. And x is 1/2. That's h. I think that's all the time we really have on this one. Are there any ones? Ooh, you know what? We'll do this guy, because this guy's pretty different. 5 is different, but it's also pretty easy, I think. 6. Consider the parabola. Determine the points that are the closest to 0, 3. There's a parabola 6 minus x squared. 6 minus x squared looks like this. And we want to find the point that is closest to 0, 3. Well, it looks like it could be here, but maybe it's like here. I don't know. It's hard to tell. The way we find the distance between two things is we use the distance formula. And the two things we're finding the distance between are the point 0, 3 and the coordinates on this function. And those coordinates are x, comma, 6 minus x squared. So the distance formula is going to be that the distance between the point 0, 3 and the point x, comma, 6 minus x squared, this is the x value, this is the y value, is y2 minus y1 squared plus x2 minus x1 squared, and we do the square root of that. Something to notice is that when you're minimizing the distance, it's the same as minimizing the square of the distance, and so we don't actually need to use the square root. If we maximize this, that makes the square root, or minimize this, that makes the square root of it get smaller. So the smaller the thing you do the square root of, the smaller that value is. So our distance, this is actually the distance squared, that's what we're going to be minimizing, is 6 minus x squared minus 3 squared plus x minus 0 squared. And I'm going to simplify this. This is 3 minus x squared squared plus x squared. So we're going to do the derivative, and we will try to find the minimum value. So this is a chain rule. It's going to be 2 times 3 minus x squared times the derivative of the inside, which is negative 2x, plus 2x. So that is the derivative. This is d squared prime. And so we want to set this equal to 0. I'm going to multiply this out. This is negative 4x times 3 minus x squared, which is negative 12x plus 8x cubed plus 2x, and we want that equal to 0. So this is negative 10x plus 8x cubed equals 0. I'm going to factor out a negative 2x. Negative 2x times 5 minus 4x squared. This can be done as the difference of two squares. So we're going to get negative 2x times 5, square root of 5 plus 2x times square root of 5 minus 2x. Sorry about this being messy here. So the critical values are x equals 0, x equals negative square root of 5 over 2, and x equals square root of 5 over 2. At this point, I would just do the candidates test. I'm going to plug this in. I would use a calculator here. And when we plug it in, we get that when x equals 0, the distance is 3. When x equals, we do that just by saying, like, hey, when x equals 0, this value is 6. 6 minus 3 is 3. When x equals square root of 5 over 2, the distance is 3.5. We get that by plugging into the distance formula. So you just plug into the distance formula. That distance is 3.5. And you don't need to actually do it the second time. This distance is also 3.5. So the minimum distance, ooh, this answer key is wrong. This answer key is wrong. The minimum distance is actually 3. The point that is closest is when x is 0, y is 3. That's the closest point. These values right here was a local minimum, but the this value was even closer. So 0, 0, 0. The coordinate is when x is 0, y is 6. When x is 0, y is 6, that creates the closest point, it looks like. That's actually kind of surprising. All right,